Hello everyone, the wait is over. Welcome to the day 8 of the LLM pre-training course where today is the day we are going to build GPT-2 from scratch. Yes, we are going to pre-train GPT-2 from scratch and I'm going to follow the pipeline which I have explained in day 7 but with a twist. Rather than starting with the dataset, here I'm going to start with the model and then I'll move on to the dataset and then creating the training pipeline. So this will be a two-part day, right? Day 8 will be about model building and day 9 will be about creating of the dataset and then creating the whole training pipeline and then training it. So this will be a two-part day. Let's start with building the model. All right. So let me put an image of GPT at the right for a reference. So right now we have a reference of what is the architecture we need to start with, right? Let's start with the most complex component out of all of these components, which is nothing but our masked multi-head attention. So let me zoom that and keep that. So this is the component which we need to start with first, right? So let me first take some imports, import torch, and then for neural network we have some other imports like from torch.nn import from import torch.nn as nn, import torch.nn dot functional as f. Okay, so these are some three important imports. Let's put it that way. Okay, let me rename the file as well. GPT-2 model. Okay, so here in this GPT-2 model we'll have GPT-2 model. Let's call it a web model and you will understand why. And for those people who find why I keep it as web model, you will have a surprise later. Okay, but yeah, let's keep it web model for now, the name. And here we'll do a def dunder init, super init is required, these are not required. So let's put a parse here. Okay, this is the architecture which we need to fill and what are the classes we want. Okay, this is the overall model class, will fill all of those. Okay, the components goes this way. Okay, we need LayerNM class, so that will be probably one of the last classes. The first one would be a masked multi-head attention class, or rather a multi-head attention class, because the mask is just a parameter which is provided. Multi-head attention class. So here also we'll just create multi-head attention nn.module def dunder init. Maybe we can this is not needed, this also is not needed. So here also we'll just keep def forward and then we'll have it as pass. Okay, so we need to import that. Here it should have been like this, def forward self pass. Okay, so what all do we have here? And then we have feed forward. Let's create something for that. feed forward class. So basically right now we are just creating a bone, like, a structure, what we need to do. This will help us to, think better. And in that module, def dunder init, here I need to remove these. This is not required. Is this here? Yeah, looking good. It's looking good now. Def forward self, and then another pass, right? So LayerNM is still there. Right? So let's copy this. I should have done that from before. People who have thought by now that, like, why Vasant hasn't just copy pasted things, please let me know in the comments, because you are better than me in this specific scenario. Okay. And if you are wondering about embeddings, right, you need not wonder, actually, because the embedding which is used in GPT are just NN dot embeddings, basically absolute embeddings. All right, so it will be easier for us to do that in the transformer model itself. So in the GPT-2 web model itself, we'll do that. And if we feel, we can also add another component like embedding. That is also something which we can do. All right, so maybe we can have that embeddings class. Okay, class input embedding, and then dot module. Here it will be I'm repeating the same issue. Copy, paste, embeddings, input embedding. Okay, so these are the things which we need to complete in this video. Okay, if we complete this architecture, we are completed with building an LLM by ourselves. Let's see one by one. Okay, so let's start with the embedding itself. All right, so where is the embedding class? Here it is. What all do we need? First, we need something called token embedding. The indentation is not that good, actually, for some reason. Self.token embedding is equal to nn.embedding. In nn.embedding, what all do we need is, I left something very important. GPT config class. What is the model name? GPT-2 web. And they'll add it as config. Here, first we need to actually provide our configurations. Let's see what are the configurations which are required right now. So let's start with something like a self dot I think with dunder init itself it's possible. Maybe we can, it is better if we have it as a separate file. So I'll create something called a GPT-2 config.py, where we can have all the constants ready. Okay, what are the things we have? Vocab size, that is important. So that is 50,257. All of these are standard. Okay, context length, what we are going to train. For now, let's keep it to 6. If possible, we'll extend it. Okay, embed dimension, or we'll call it as D model. Usually D model is, let's have it as 512. Number of attention heads, let's have it as 8. Number of layers, maybe both 6. Okay, let's keep 6 for both. Dropout, will be 0.1 dropout probability. Okay, these are some of the configs we require, because for example, just see now here, I'll import those from GPT2 config, import star. I need to import all of those values, and here I'm going to use that. For embedding, if you see, we require the number of embeddings, which is your vocab size. Okay, for how many number of tokens you need embedding, that is your vocab size basically. So here I'm going to initialize that. Self dot vocab size is equal to vocab size, and then we can call that here. Okay, and then the next one is d model. Okay, which is your embedding dimension. Self dot so right now we are getting our d model. D model is d model, and then we'll also provide that because our embedding dimension is important, right? I hope the size looks good now. No, with this on the side, I'm not sure if it was clear before. So yeah, this looks good, better. Now let's have the position embedding. Positional embedding will be an n embedding again, but here just guess now, what are the things you will be providing. If you guessed self dot what was the name I kept? Context length. If you kept it as self dot context length, then yes, you are right, because we are encoding the position, right? So self dot context length will be equal to context length, and then we'll provide that here. Along with that, self dot d model, that is no magic here, right? So it is going to be pretty simple for us right now. Okay, so in everywhere we need torch dot device. So device is equal to CUDA if torch dot CUDA dot is underscore available, else CPU. Okay, so device is very important everywhere. Actually this definition should not be here, it should be rather here. Import torch, then we'll have it here, device, right? Now in everywhere, then that will be imported. Self dot device equal to device. That ensures that you don't run into any issues. So let's see what we need to do for that now in the forward section. Okay, so here it will be input IDs. Okay, let's have it as X. Okay, so it is going to be batch size and then sequence length. Why? Because it will be for example, one sentence with 10 tokens. That's all. The embedding is not still computed, so we are going to compute that. So only it will have two dimension, so we will have its extra shape. Now we need to create token embeddings. Token embeddings, let's have it as X token embedding. Okay, X token embedding is equal to self dot token embedding of X. Okay, and then here what we can do is we need to initialize another thing, which is self.positions, which will be um, I think it is better if we do it in runtime itself. Yeah. So what we can do is positions will be equal to torch dot arrange of arrange is a function which will create numbers from start till end. Okay. So right now it is like, from 0 to max length, right? So we need to provide that. So it is going to be self dot context length. No, not context length. Self dot sequence length. Um, yeah, sequence length is what we need to provide here. And then you need to provide device here, which will be self dot device. Now you have the positions, you need to embed this. Okay. Let's have it as position embeddings. X position embedding will be equal to self dot position embedding of positions. Okay. So now we need to add both of these. Okay. So X input embedding will be equal to X token embedding added to X position embedding. Okay. And here you need to note something, which is we haven't added a dropout yet. Usually we need to add a dropout because that regularizes things a bit. So we'll initialize that as well. Okay. But if we have the same name for everywhere, we'll just get confused. So we'll have it as self.dropout for embeddings. Okay. And here it is going to be nn.dropout, and already we have the dropout probability. So it is going to be self.p equal to dropout p, and then we need to provide that here, self.p. That's all. Okay. So now the input embeddings needs to be normalized. So X input embed, let's put return here itself. Return self dot dropout embedding of X input embedding. Okay. Now we are done with creation of input embeddings. Next, let's go on with multi-head attention. Okay. I said we will start with that, but input embeddings demanded it, so we just did it. Let's do with multi-head attention now. With multi-head attention, what are the things we require? Let's see that. Okay. So here, if you remember from our transformers construction itself, so it will take some things like D model, which is our embedding dimension. It will be of int type, num h, so number of attention hints it wants. So it will be also int. What is the context length you want? So that will be again an int value. Dropout. So actually what you can do is you can hard code these from here as well. Okay, that is also something which is a very good practice. But usually we keep input embeddings outside. All of these will be encoded inside. That's why I kept it. But we can also do this as well later, like for example keeping this here. That will look neater actually. Okay. Vocab size, D model, context length, device, and then dropout p. Okay. So if I do this, it will be even better to look actually. because anyway you're gonna initialize these parameters from the GPT-2 model, so it will look better. Let's keep it that way. Okay, so vocab size will be an int value, d model will be an int value, context length will be an int value, device will be torch dot device, and then dropout p will be a float value. Okay, now let's start with multi-detention again. Again we are just jumping, sorry for that. First thing we need to see is here write an assertion statement to make sure that d model is divisible by the number of hits. So for example, if I go Python, what was the consideration we had? Let's see if that works actually first. 512% 6. So the remainder is 2, which means it won't work. Let's try for 8. It is 0, which means it will work. As simple as that. Okay, because you are going to split your embeddings across the heads, right? So it is very important that your embedding dimension is divisible by the number of heads. So let's keep both of these same. Number of layers also 8. If you keep 6 as well, it will work for number of layers, but number of attention heads needs to be 8. Okay, so yeah, right now this should work for us. Here with assert, you need to provide a statement as well, where if this statement fails, what it will say is d model is indivisible, or something like d model should be divisible by num h, something like this, so that if you click some other config, you will just get a warning stating that this is an issue for you. Okay, without even executing the whole and then wasting some time. So let's add all of those values in here. So it is going to be self dot d model will be equal to d model, and then self dot embed dimension will be equal to self dot embed dimension, not embed dimension, num heads, sorry. So it is going to be num heads equal to num heads self dot context length equal to context length, and then self dot p, let's have it as dropout, attention dropout is equal to dropout. Okay, so these are the things which is required. Right now self dot qkv, why we are initializing like that? Because in the official implementation as well, all of these would have been created together as a single one, so we'll also try to do that, right? So it is going to be nn dot linear, where it will be d model comma d model cross 3. Okay, basically we are saying that it will be 3, so that will be splitting at that dimension. Okay, and here we need to provide a bias as well, stating that it is false. Okay, we don't need any attention bias. And then we need a projection. Actually what in GPT official name would be something like CATTN. This is how it will look like actually. Maybe we'll do it in one future time, where we'll convert this architecture in such a way that this is compatible to Hugging Face. We'll do it in some time. Okay, so let me know if you want that in the comment section. I'll try to do that. Self.projection will be equal to nn.linear of d model to d model. Okay, basically this is to comprise all of this information together. Okay, next we have self dot attention dropout equal to attention dropout. Oh, we already initialized that, right? I think it should be simple. Yeah, this is good. Now let's implement the forward function. Here we'll get x. Okay, that is usual. What are the things we required here? Batch size, sequence length, and embedding dimension, or we usually call it as d model, right? So d model, both of all of these three are there. So why? Because you have embedded it already, right? So embedding dimension will be added, and then it will be provided to the masked multi-head self attention. Basically, that is what we are creating here. So it will have 3 dimensions rather than a 2 dimension, how it was for embedding. Okay. Now, first we need to make this, with weight layers. Okay, we need to add some weights to this. So we need to call self.qkv of x. So basically right now it would be something like, this batch size, sequence length, d model will be converted to batch size, sequence length, three cross d model. Okay, so these will be the things there. Now we'll make this in such a way that this is, available for multiple heads. Okay, so for that we'll call qkv equal to qkv dot view. View is basically like a reshape function. Basically what is the dimension we require is from this. Okay, I need to take out this. This needs to be converted like batch size, and then it should be num tokens for query key value, so 3, and then number of hits, and then head dimension. Okay, so we haven't computed the head dimension. Let's compute that. Okay, so it should have been here. Self dot head dimension will be equal to self dot d model flow divided by self dot num hits. Okay, so that was also something which is required. Now here if you see, we need to do this, right? How are we going to do this? We need to view it in such a way that it should be batch size first. We already have that. So next we need the num tokens, right? Number of tokens is nothing but your sequence length. So it is going to be sequence length, and then it should be 3 hard coded, and then self dot num heads, and then self dot head dimension. Why is this even possible? First, if you see, it would have been 3 cross d model, which will be something like a 3 comma, which you can make it actually. If you do it step by step, right? You can also make this where you will get this input, okay, and then you will convert it as 3 comma d model, but we are doing it in a single step. Okay, that is what is happening here. So right now it is 3 comma number of hits comma head dimension. So you have the values for QKV together, but we need to have it as 3 as the first, because then only you'll be able to separate as QKV. Okay, so for that, what you need to do is, so basically how I require here is, I'll show you. From here, it should become something like this. Okay, I'll change it from here. 3 comma batch size comma sequence length comma number of tokens comma head dimension. Okay, basically this 3 should come first, right? So that is what is required. So for that, what you need to do is use a function known as QKV dot permute. There is a function known as permute in Torch, where what you can do is you can just change the dimension. Okay, so for example, 3 was at the second dimension, right? 0, 1, 2. So 2 will become first. I need 0 next, and then I need 1, right? So 1, and then what I have here, 2 is already done, so 3, right? So it will be 3 and then 4. Basically the array will be rearranged. Okay, so it will be 2, 0. Just let me check first. Once it was like this, 2, 0. Yeah, that is where I got confused. I was just thinking. So it should have been 20314. Okay, why? Because 2 is basically the number, which is QKV, but you need to split it across head, right? So it would have been 2 batch size, and then the number of heads to which the tokens will be applied. Okay, so it would be like number of heads first, and then sequence length for that. Okay, so this is how it will be splitted now. Now what we'll do is we'll just have it as query key value from QKV. Okay, now how it will be looking like is, I'll just copy this. So it will be like 3 star all of these. Okay, for each of those there will be a batch size, num head, sequence length, head dimension kind of a structure. All right, so here we'll see if there is a dropout or not. Okay, so we have a dropout here. Okay, always there is going to be a dropout. I need to put as float here. So what we are going to do is, instead of writing scale dot product attention by ourselves, which will be like a learning curve for us, but it is not very efficient. We have already seen how to write that, right? Torch has optimized it better in something known as NN dot functional. Okay, in functional itself, if you see f dot scale dot product attention, it will have a value, and if you see here, they would have implemented it. Okay, they would have implemented it, and that is what we are going to use. Okay, so you can see what are the things it requires. Query, we have it. Key, we have it. Value, we have it. Attention mask, we do not need to provide, because if we say is causal, it is going to work. And then dropout probability, it is going to be something which we are going to provide. Is causal is going to be false. Okay, these are not required, right? So it is going to be, let's put it as attention underscore x. Okay, x is computed with attention. Basically this is a context vector which has some attention to it. So nn dot functional, already we imported it, right? So it will have it as f dot scale dot product attention of query equal to query key equal to key value equal to value, attention mask equal to none. We'll see what we need to do, like if we want to make an attention mask, because if you see, when you send is causal to true with the context length and all, right, it will try to generate the mask by itself, basically inside. Dropout p will be self dot dropout, attention dropout, and then is causal, we'll get that as well from the user. Basically is causal is going to be true, right? For us, we are not building transformer, so let's have it as is causal to true. Okay, so now we have computed the attention, but if you see this attention, what shape it will have is, it will have something like a batch size, num head, sequence length, head dimension, similarly like how it was before, but we need to combine those together so that it is concatenated us from the multiple head to the single head. Okay, that concatenation step, how it will look like is concat attnx will be equal to attnx dot transpose of 1 comma 2. Why? These need to be transposed. Sequence length should be first, num head should be second, so that num heads and head dimension will be combined together. Okay, we need to make sure that those are contiguous, okay, because we are combining it from different places, so those should be contiguous, and then we'll view it in such a way that batch size comes first, sequence length comes second, and then it will be D model. Okay, where do we have D model here? Yeah, so it will be D model. Okay, so basically we have combined it. Now we need to send it via projection. attn projection x will be equal to self dot projection of concat attn x. Okay, right now I have my attention completed, so I just need to return this. So here I didn't mention it, right? So here it will be a two-step process. It will be batch size, num head, sequence length, head dimension 2. Batch size, sequence length, num head dimension, num head dimension, which will be combined to batch size, sequence length, D model. Okay, this is how it works as far as the attention is concerned. All right. Here it is just a linear layer, so the shapes are not going to change. Okay, now let's see how to implement the feed forward. So right now we are in feed forward. Let's do LayerNM later, like that is a common thing, right? Let's have it later. So for feed forward, what are the things we require? Let's see that, right? So here you will need something like a D model, and then you need something like a DFF. Okay, so what is DFF? In D model, we say embedding dimension, right? There is a dimension specifically for feed forward itself, which people usually call it as intermediate dimension. Usually it is D model star 4 times. Okay, I'll have it as a relative, but that applies only if your model is very small. If you go for like a big model, it will have 4096, you need to have 16,000. That is not something very feasible. But like it is usually larger the better, because when it is a larger network, it can understand the information which the masked multi-head attention has captured better. Okay, so we need D model and DFF. Other than that, we don't need anything actually. So now how we can do this is, it will have two linear layers. Okay, self dot fully connected layer 1 will be nn dot linear of self dot, oh, I should have initialized that, I forgot it. Self dot dmodel equal to dmodel, self dot dff equal to dff. Okay, so that is feed forward dimension. Let's have it there. So it is going to be self dot dmodel cross self dot dff, and the second one will be the straight opposite. Okay, fc2 will be self dot dff comma self dot dmodel. You're up projecting it, you're down projecting it. It is better if you write it, like this: up projection, down projection. That is where you'll have those, like, understanding clearly that this is how it works. Okay, so we have self up projection and down projection. Along with that, we need a dropout. I forgot that. So dropout would be there. So this is gonna be an int value. This is gonna be an int value, and this is gonna be a float value, right? So self dot dropout will be nn dot dropout of self dot dropout. This is like the thing which we did with input embedding. Let's just put it as ff dropout, like how we are maintaining it, right? Okay, we haven't initialized that. Self dot dropout equal to dropout. Okay, so self dot feed forward dropout is also ready. Now we need to add another thing, which is self dot gelu. Gelu is the activation function which is used in the paper, so we'll also use that. nn dot gelu. How it works is, basically you have your input x. Okay, I haven't added the type there. Torch.tensor. Where is tensor? Here it is. I should have added those there as well. X is to torch.tensor. Do I have anywhere else? Sorry for the disturbance caused. So I'm just adding typecasting everywhere so that it will be actually easier. So if for example there I was doing something like a x dot shape, right? So if I did now, it will show automatically. That is a better way. For example, it was qkv here. If I had something like a qkv is to torch dot tensor, you'll see a difference now. See, qkv dot view, qkv dot permute. It is always better to have a typecasting, because with VS Code, right, it will give you the functions directly. It will make your life easier. So I usually do that a lot. So it is going to be torch.tensor. So given an input, it is going to be very simple. We are not going to get batch size, sequence length, nothing. Okay. So self dot not approach x will be self dot up projection of x, and then we'll send it to gelu, self dot gelu of up projects, and then down proj x will be self dot down projection of up projection x, and now we'll drop out it. ff out will be equal to self dot ff dropout of down projection x, and then we'll return that. Return ff out. Okay, so right now our attention is done, our feed forward is done. So basically it would have been at the dimension. So whatever it was, so let's say it was D model, right? So it would have been something like 512 converted to 2048, because that is what is our DFF, because it is basically the 4 times. Okay, and then another converted to 512. And the good part is you'll learn something out of this. That is why it is there. Now let's see how you can implement the LayerNM class. Okay, add and LayerNM is different. Okay, adding is something different, and LayerNM is something different. Okay, right now we are just seeing how to do LayerNM. Okay, add and LayerNum will do it in the model itself directly. So for LayerNum, the function which we are going to use is a simple z-score function. Okay, so for that you will find the mean, the variance, and then you'll do a standard root for variance so that you'll get the standard deviation. But here with that we'll add an epsilon. So the formula would be something like this. Okay, this is what we will be implementing here: x minus mean by standard deviation. Okay, that's all. And then here we'll just add some other values after this. Okay, so let's say you get an output here. You will be doing scaling. So it is like alpha star x plus beta. Okay, so it will be alpha star, let's say it is norm x, it will be converted plus beta. Okay, this is the formula basically for LayerNM. So for LayerNM, you need one parameter, which is EPS, and that is float. Okay, and here EPS value will be like epsilon value, basically 1 e minus 5 or 1 e minus 6 is a very common value. Okay, you can also hard code it there as a keyword argument rather than a just normal argument, because if it is not provided, it will take a default value, right? So here we need two things. One is epsilon being initialized. Along with that, self dot alpha, which will be nn dot parameter. So these parameters are learnable. Okay, that alpha and beta are learnable. So if you are wondering how the theory of all of these work, please make sure that you watch the transformers theory video, because I've explained each and every component in very much detail as much as possible. Okay, so how nn dot parameter will be initialized with is, it will be just torch dot ones of D model that needs to be provided here. I forgot that. So it is going to be D model is to int comma epsilon. Why I put D model before is not because it is a very important value, because arguments come first and then keyword argument. Okay, if you put D model first and then epsilon first and then D model second with values for epsilon, you will get error. Okay, so we need to get D model. So it will just, here what it will do is it will just create a 512 number of ones. So it will be the same for beta. Basically the normalizations will happen at the embedding dimension. Okay, so here what we need to do is first find the mean, right? So mean will be equal to x dot, we need to provide x here. X is to torch dot tensor. If I see now x dot mean, simple, dimension will be -1, because at the last dimension, which is embedding dimension only, I need mean, so I keep the dimension to true. The variance will be equal to x dot var. So this x dot var function will compute the variance. Okay, again we'll be doing it at dimension -1, which is the embedding dimension, which is the last dimension basically. And then we'll set unbiased to false. Okay, and then keep dimension to true. Okay, so here we are going to normalize the x, right? So x normalized will be equal to, see the formula, x minus mean. If you remember the BODMAS rule, subtraction will happen later, but x minus mean should happen together. So we need to add a bracket there. X minus mean dot square root of, here it should be square root. Okay, because standard deviation will be square root of variance, but here just rather than square root of directly to variance, we'll add something like a epsilon value to it. Okay, so self epsilon, let's put it as learned x normalized. That would be a good way to put it, because we are adding two learnable parameters for that, right? Self dot alpha star x normalized plus self dot beta. This is where the normalization becomes a learned normalization. Okay, learned x normalized. Okay, so this is how the layer norm happens. So right now, if you see, our embeddings is done, layer norm is done, feed forward is done, multi-detention is done. We are coming into the final and the most interesting part, which is to construct this architecture here based on all of the things we have created here. Okay, this is where it is going to be very interesting. All right, so first here I need to take out all the values which are there in config. Okay, here I'll just put it as a 2 tab. That is when it will become easy for me to initialize things. Okay, self dot vocab size will be vocab size. Self dot context length will be equal to context length. Self dot, what is it, d model, yeah, d model will be equal to d model. Self dot num heads will be equal to n heads. Self dot num layers equal to n layers, and then self dot dropout probability will be equal to dropout probability. Self dot feed forward dimension will be equal to feed forward dimension. And just it is boring, you know, like it is always boring. Self dot APS is epsilon equal to epsilon. Self dot device equal to device. Okay, every initialization is done finally. Okay, now coming on to initialization of those, which is self dot yeah, just now I forgot. If you remember, this will be a stack, right? And that is why I wanted to add that here. So it will be something like GPT block. We need to create that. Okay, it will be GPT block, which we need to create right now. Oral model classes later. Still the fun part remains actually. GPT block class GPT block nn dot module def dunder init of self super dot dunder init. So here we need to first integrate those. These are not required right now. We need to integrate those here. So here, what we are going to do is we are going to just combine these blocks alone. Okay, that is what we are going to do. Here, what are the things we required? Actually, here we don't require dropout in feed forward. Okay, let me put it as feed forward out here itself, because those dropouts will be done in here itself. Okay, we don't need dropout here. I'll just take this out. Yeah, looks good. So we need to first take out all these values, right? So what I'm going to do is I'm just going to copy these. Okay, paste it here, because I'm not going to provide the parameters again, right? So I'm just going to take all of these, have it here, and then initialize my architectures. Self dot multi head attention will be equal to multi head attention of self dot d model. What are the things? Self dot num heads, self dot context length, self dot dropout. Okay, so these are the things required. And then for feed forward, what are the things again which is required here? Feed forward, which will require self dot d model, self dot dropout. Oh no, dff, I guess. Yeah, here vocab size will be required, I guess, because we are not initializing embeddings. Okay, and then we require two layer norms. Okay, so it is going to be self dot layer norm 1 will be layer norm which we created now, self dot d model self dot epsilon. We are initializing it as two stages, because if you remember, those are learnable, right? So that is why. Here you can see layer norm 1, layer norm 2, mass multi attention, feed forward, all are done. Now this flow which you are seeing right now, we need to implement that in the forward. Okay, let's see that. Def forward self and x, which will be a torch tensor. Here first what we need to do is take the x value, like, before norm, something like that. Before norm x will be equal to x, self dot norm 1 of x, x norm, x1 norm, probably x norm 1, we'll have it as x norm 1. Okay, and this x norm 1, let's have it as x itself, it will be easier to maintain the stage actually. X here, and then we'll send that x to self dot multi head attention of x, and here if you see, it will be batch size, sequence length, embedding dimension, the same shape will retain hereafter. That is not an issue. That is one of the main advantages actually. Here we need to initialize a dropout. Okay, so self dot dropout, let's put it as norm dropout, or what it is. I'm not sure. Let's have it as add the ln drop. Okay, add ln drop, because it is used in add and layer norm section. Self dot drop out p. Okay, so I need to call that self dot add layer norm drop of x. Okay, so right now here we have, okay, we got x before norm, we have normalized it, we have sent to attention, we have got the output which is normalized. Now we need to add that with the before norm. Okay, we have a before norm here basically. Actually, I guess the norm one shouldn't be done here. Let's see. Okay, maybe I think before add would be something, because this is a confusion where, like, every time I implement, I'll get this confusion whether I need to add before or after. Let's see if this kind of an architecture works. If not, we'll go for having this before norm x later. Okay, before norm after attention. Okay, before norm after attention. Here I need to first add that. I left that. So x will be equal to x plus before norm I, before norm x. Okay, so that is how x will be here. Before norm after attention. I think even here before attention. This is good. I'll have it as before FFN. That is better. Okay. Now it will be LayerNM 2 of x, self dot feed forward of x, add LayerNM drop of x, and the x will be equal to before norm before FFN. Here it is. Okay, this is how it will be combined. Okay, and finally that softmax and all, we'll do it in the main function. Okay, right now I'll just return the x here. Okay, we need to replicate this for num layers. That is why this is kept as a separate block. So self.gpt block will be equal to gpt block, and then other than this, what are the things you require? We will require a final layer norm, self.final layer norm will be equal to nn dot layer norm. No, why nn dot layer norm? We have already initialized it, right? Layer norm of self dot d model. Okay. So here, if you see, the GPT block is a single block, right? But like I said, this will be for n layers, right? So we'll just replicate it, all right? So what we need to do is, we'll just call something called nn.sequential of, here we need this, we'll have it for later. Okay, actually it is always fun to combine together rather than coding it from scratch. The fun part is always when you combine these things together, because that is where you feel like you are really constructing the architecture. So how much we want? So for underscore in range, so basically this star will replicate. Okay, so for range, the num layers, self dot num layers. Okay, for the number of layers, we'll have the number of blocks. Okay, star will make sure that all of these are combined together in sequential, and sequential is like, one will be sent to another. You need not manually send one layers to another. So thanks to thoughts for that. Self dot final projection, let's put it that way. Here you can see, right, there is a final projection, this place, right? Actually it should not be embedding t, it should be named as projection. Okay, so the embedding t, it is named as like that because that is where you will convert your embedding to vocab. Okay, so how it will look like is something like this, because here you are combining, like, making your tokens as embedding. It is the reverse here. You are making your embeddings as token. That is why it is named as embedding transpose, but it's not like just that. It is like nn.linear of self.d model across self.vocab size. Okay, and make sure that the bias is set false here. Okay, Here I think I need to provide that here as well, if I'm not wrong. Where was that feed forward? Let's see if there is a training issue, we'll understand. Usually if you keep bias, right, there will be an issue while training. So how the forward of the transformer will look like, first we'll compute the embeddings, right? So we need to take that as well. I didn't take that here, right? So it should be self dot input embedding will be equal to input embedding of self dot vocab size, self dot demodel, self dot context length. It is just going on, but it has been fun building it from scratch. Just let me know how much you enjoyed today, because I enjoyed this very much, implementing it from scratch. So how are we combining it? First, you'll get the input IDs, right? So let's put it as input IDs. Okay, it will be a torch tensor list actually. Torch dot tensor. Here, what we'll do is we'll compute input embeds. Let's put it that way, because that is only gonna make sense. Input embedding of input IDs. Now we have computed the input embeddings. Now it is time to pass through the transformer blocks which we have created, which is the GPT blocks here. Okay, so the GPT blocks are going to be providing something like maybe GPT out. Let's just put it that way. GPT out is equal to self dot GPT blocks of input embeds. So that will give us a value. Okay, so here we are going to now say, see, the embeddings are going to be projected to the tokens again. So usually we call it as logits. Okay, so I'm going to call it from now. There is going to be normalization, that is later. Okay, logits is equal to self dot, here actually we need to first do a normalization. GPT out is equal to self dot final layer norm of GPT out. Okay, and then here logits will be equal to self dot final projection of GPT out. Okay, so here we have the logits. We'll just return the logits. If you're wondering where the softmax happens, the softmax happens when you do decoding. That will be in the subsequent videos. Okay, in this video, which is day 8, we have just implemented a GPT-2 model from scratch. Okay, in the next video, which is day 9, we'll create a torch dataset, a torch data loader. We'll collect some datasets from internet, mainly from Hugging Face, which are pre-training datasets, and then we'll just process it. We'll make sure that we write a pipeline which is good enough to handle large amount of dataset. And then what we'll do is we'll create a training pipeline, and then we'll create the model which is pre-trained for a specific use case at the later part. Okay, this is the way forward. And yeah, right now we are just moving on to advanced points. Okay, so yeah guys, I hope you all like this video. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in another amazing video. If you like me calling amazing, please hit the like button. Okay, cheers.